In this video, I'm going to derive the expression for the induced E.m.f. in a straight conductor as it cuts through a magnetic field. Before we do that, let us recall Faraday's law of electromagnetic induction, which states that the magnitude of the induced E.m.f. is directly proportional to the rate of change of flux linkage or to the rate of cutting of magnetic flux. Recall also that the Faraday's law of electromagnetic induction is more commonly written in the form of E equals to minus d phi dt. For this case, we are going to use this second form of Faraday's law, which is the rate of cutting of magnetic flux, to get the expression for the magnitude of the EMF induced. Let's consider a straight conductor that is moving at a speed v in a uniform magnetic field B. After some time, it has moved to this new position. So what do we mean by flux cut? We can imagine the conductor as a blade of a knife that is moving through this field and the field lines as grass. As the blade moves through, it will be cutting through the grass. Since there is flux cut, Faraday's law predicts that there is an EMF induced across this conductor, and the EMF induced, its magnitude, will be equal to the rate of flux cut. Now, to find the rate of flux cut, we will first need two quantities, the magnetic flux density B and the area that the conductor has cut. Let's assume that it has moved through a distance of delta x in a time of delta t. The area of the field cut by the straight conductor is this red area here and is therefore equals to L times delta x. Hence, the magnetic flux cut by the conductor is given by B times the area that is cut, and it is BL delta x. The rate at which flux is cut is therefore written as the total flux cut divided by the total time taken, which is BL delta x divided by delta t. Now, we know that delta x over delta t gives us the speed v. Hence, we can write this as BLV. Therefore, the EMF induced, which is equals to the rate of flux cut, is E equals to BLV. Note the following things. We have dropped the negative sign for the E equals to minus d phi dt because what we simply want would be the magnitude. Secondly, this equation is for the case when the conductor and the magnetic field and the velocity are all perpendicular to each other. Hence, we commonly write the equation in these forms to remind ourselves that when they are not, we simply need to resolve the most convenient physical quantity and use the component that is perpendicular to the other two. With this, we end our video.